So I have a really big presentation. So in Las Vegas, I definitely ran out of time. So just in case, my email address is LYD, my last name, first initial at VMware.com. Especially on the troubleshooting part, I have a 200-page plus document with a lot of details that I haven't published, right? And I have no official plans to publish it yet because it's not fully reviewed. So if you reach out to me on my email address, I can give you a copy, okay? And then from content-wise, I know a lot of it you will have a lot of questions. In the last couple of weeks, I've spent 3 one-hour sessions with the same customer on just 2 of these slides, okay? So just know that the content exists, and if you need help, reach out to me, okay? This session is not about how to get started in NSX, or if you figure out how to if you misconfigure something, how to figure out if you've done something wrong or whatever. This is about you having NSX up and running, and how can you tell how well it's working, okay? So first of all, we'll start with an overview of how NSX's control and management plane works, and then what you have to monitor within that, right? And then we'll talk a little about the edge data path performance, but the majority of this content that you'll be interested in will be in the ESXi data path, okay? And this will be relevant to you regardless if you're running NSX or not NSX, as long as you're running vSphere networking with NSXV, NSXT, or whatever, this all applies, okay? And then if we have time, we'll run through the last few slides. Otherwise, you'll get a copy of it or reach out to me, okay? So when you have NSX up and running, right, you have installed your NSX manager, you're the admin, and then you have some ESX hosts that you have prepped, and you have some edges that you're prepping. And the most important thing is once you have these prepped, the word prep means that the NSX manager is connected to your ESX host and your edges, right? And you will have these communication channels up. There will actually be 2 TCP connections, so you should be monitoring for that, okay? And these will be always up. If they go down for any reasons, obviously there's going to be a health issue. Now, once you have your edges, you create your edge cluster, right? The moment you create that edge cluster, they will create BFD tunnels between themselves to do health checks, okay? And BFD health checks are 1-second intervals. Obviously, if after 3 miss hellos, you have failures, okay? So monitor BFD. And then you go and create your logical configurations, whether it's routing or switching, whatever. So you look at this picture, nothing has changed yet, okay? And then you go and create VM, right? And we've broken down the VM into minute steps here. But the moment you create your VM, still nothing has changed, okay? Then you say, I want to connect my VMs to the network. At that point, NSX will say, the controller will say, I have realized a logical span or active logical span, okay? And that logical span encompasses where your VMs are connected and where you have distributed routing instantiated to service those VMs, right? The moment that active span comes up, NSX will ask these transport nodes to create BFD tunnels between themselves, okay? And the BFD tunnels will only be up between the edges and the hosts that are participating in providing services to your VMs, right? In this picture, ESXi 3 is not involved because there are no VMs active on it, right? So that's the definition of the active span will cause BFD tunnels to be created. So you should be monitoring your BFD health, okay? Now, before we talk about how to monitor that, right? The primary component in your NSX environment is your NSX manager cluster, right? So you should be monitoring the health of that. So in general, when you monitor your VMs today, right, the NSX managers are just VMs, right? You'll be monitoring CPU usage and memory usage in general, right? That's what most people do. Now, I'm asking you not to do that, okay? Because CPU usage, when you look at vSphere or VROps, when they monitor CPU usage, it gives you an aggregate of all the CPUs in the system. So it doesn't, most of the time it goes up to 100% or 200% sometimes, depending on the number of CPU cores you got, right? So don't monitor CPU usage. And even on a single threaded system, you could have one CPU that's at 100%, right? Your process is running well because it's using all 100% of your CPU. It doesn't mean that your system is overloaded, okay? So the better metric for monitoring your NSX manager usage is the CPU load, because the CPU load is a measurement of application demand versus CPU availability, right? So you should be monitoring your CPU load, okay? And track it over time to see whether it has grown, right? I won't tell you what your baseline number should be because it depends on the size of your configuration and scale and so on, right? So everybody will have a different baseline. So, but you should be monitoring over time to see whether it has grown, right? Now, what about memory? Okay, definitely so there is some value still to monitoring CPU usage, but there's zero value to monitoring memory usage on your vCenter or VROps, okay? Because in the NSX manager, pretty much all of the critical applications are running in Java, okay? If you're not familiar with Java, the way it works is each of the processes, when they start, they run inside what is called a Java virtual machine, okay? And the Java virtual machine is pre-configured to use up to a maximum amount of memory. So we call that the Java heap size, right? So when the application within that JVM reaches a certain amount and there's no more available heap size, there's a garbage collector that frees up memory within that heap, okay? But the JVM will request as much memory as it needs up to the maximum configure value. So if you just track the VM memory usage, it will look like it grows and it never goes down, right? So if you monitor the memory usage, it will look like you have a memory leak, okay? But there's a garbage collector that runs inside the JVM that will free up memory. Now, how do you really say, I have memory available within the JVM, right? So the easiest method to measure that is your load average, okay? Because the garbage collector will run more often when there's less memory available within the heap, okay? So in a lot of the biggest environments that we've seen, it's the garbage collector that actually uses up most of your CPU rather than your features. Okay, so check that, right? So the only metric you need to monitor for your manager is CPU usage and memory. So the CPU load for both as a proxy for the CPU usage and memory usage. Okay? Now, I've shown two APIs here. They're the same. They give you the same data, just one's older than the other one. But this API will give you. Earlier when I talked about the active span, I showed you all those connections in the BFD tunnels, right? This API will give you a summary of all of the connectivity and health of BFDs for all of the transport nodes, okay? So here I've chosen to only graph the BFD health. So obviously your network's not gonna look like this, right? This is a measurement of the number of BFD tunnels that are down, right? If you chart this in your healthy environment, it should always be 0, right? I chart this for a lab where I introduce failure, so I see something, but you should never see something, okay? But this is the API, if you have to monitor any APIs, this would be the one to get your health, right? And you should be tracking it over time. So when customers ask me, whether your NSX environment is running healthy or not, it's mostly about performance, okay? So on the edges, the first part that we look at are the NSX edges, and we have bare metal edges and VM edges. The monitoring is pretty much the same way. And the meat of this presentation that will follow the next couple of slides is going to be on ESX that applies to VM edges, okay? But in terms of within the edge itself, there's no difference between how you monitor a bare metal edge or a VM edge, right? Going back on what I said about monitoring CPU usage within the NSX manager, never monitor the CPU usage of your edges through vCenter or VROps, right? Because the edge is running a forwarding engine called DBDK. So DBDK will go and request CPU from your VM, from the edge appliance, whether it's bare metal or VM, right? And the edge appliance will give CPU to DBDK, but it doesn't mean that DBDK is consuming it, because DBDK will request it in chunks. Okay? In bare metal, it will always request 100% actually. So if you monitor your CPU usage in your bare metal edge, those cores are always 100% used, even if you're forwarding 0 packets. Okay? The VM edges are not, they won't request 100% all the time, but it will be high. Okay? So what you should be monitoring is the actual DBDK CPU usage, which is what we represented with the data plane CPU stats. Okay? So you should be monitoring that over time. Again, what I tell customers is if you chart your CPU, the data plane CPU usage, if you get to 85%, you need to start remediating or looking at options, right? Because network is never steady state, it's always bursty. So when you go above 85% or 90%, it's very likely that during the day, when you're not monitoring, there is a burst of traffic that is exceeding 100%. Okay. Now, given that you're monitoring your CPU usage, how efficient is it? Okay. Many customers ask me what the expected throughput of an edge is. Again, I won't give you a number because it depends on your configuration, right? But if you really look inside the engine, even though we're running DPK, within DPK itself, we have 3 forwarding modes. Okay. When a packet, to read through this, when a packet enters your edge, it'll immediately look up what we call a microflow table. Okay. If the microflow table works, then that's the most efficient way to forward packets within the edge. Right. If it misses a hit, then it'll go to the megaflow entry, and if it hits that, and depending on whether your traffic qualifies to be installed as a microflow, it will install a microflow entry. Otherwise, it will just forward it, right? And if the megaflow also misses, then it will go to what we call a slow path. Slow path is similar to what you've learned in traditional routing, right? It gets your packet, breaks down the header, looks up the forwarding table, and do a rewrite, and so on, right? So that's what slow path means. Now, most of you, if you follow our best practices, will not be using microflows, right? Because microflow, the flow table is the signature of the flow, right? The signature includes both the headers and the next hops. So if you have more than one next hop, then we cannot embed it in one signature, right? So if you have ECMP, if your edge has more than one tab, it won't qualify for microflow, right? Now, the flow table, each data path CPU has 256K entries shared between microflow and megaflows. Actually, I have an output in the next slide. So if you get the flow cache data for each CPU core, I've shown one core here. There's a number here on 256K number, right? It'll show you how many are used. That's fate, okay? Because the way entries are created in the table is, it's like a spreadsheet, right? When we write into a row and it gets invalidated, we don't erase it. But the data is still there, it's just marked as stale. So, but when you look at this table, it'll show, because there's data there, it'll show that it's used. So the number doesn't mean anything, right? So the most important thing to monitor for your flow cache will be the hit rate, right? Remember, most of you will be seeing megaflows and only, your microflows will not be used, okay? And then if your edge is running close to 100% on your cores, right, your packets will be buffered up in the ingress ring buffers. And then if you have enough packets buffer up, then you'll start dropping traffic, okay? The RX misses represent the ingress buffer drops. The TX drops represent the egress, okay? Now, if you really, when your edge will have multiple CPUs, right, for forwarding packets, and the edge will hash traffic based on the header to the cores, right? So if in a typical enterprise environment, your flow, you should have enough flow entropy where all of the CPU cores are pretty much evenly used, right? But if you suspect that you have an elephant flow, we cannot split one single flow to multiple cores, right? So you have single flow, then your distribution would not be even. So this will be one way to find out whether your cores are evenly used, okay? This is an example showing a medium VM edge where there are 4 data path cores, right? The number of queues will equal the number of cores that you have. So the largest VM edge will have 8 data path cores, and your bare metal will be many more. Okay? Now, a packet comes in, how do you know if your edge has successfully routed it? Okay? The way to find out is in debug mode, we have this data path counter. You set an ACL rule. The ACL rule matches your packet header, right? And it's a unidirectional rule, so if you want to see the reverse flow, you have to set the reverse flow. Right. What this will give you is the number of packets matching that flow coming in and the number of packets matching it that leaves, right? So if any packets are dropped, you will be able to see it through this method. Okay. Unless you're running the latest 412 version, your ACL rule cannot do protocol or port numbers, right? So you upgrade to 412, the rules will let you have that capability. Now, if you call for support, okay, and you have an issue with your edge and somebody wants to go and do packet captures on your edge, don't let them do it. Okay? The reason is because the packets are being forwarded by a TDPK engine, right? And the packet capture is implemented using TCP dump on the Linux kernel, okay? So in order for packet capture to work, we have to punt the packets out of the TDPK engine into Linux. That performance will be at least 1 order of magnitude lower than what DPDK can do, right? So by troubleshooting using packet capture, you may be causing an outage in itself, right? So unless you know for sure that your packet rate is low enough where you can do packet captures, don't do it. Okay. So if you have to look at per packet, go to the previous slide where I have, you can set up the ACL rules to look at packets, right? Now, how many of you have heard of NAP or install NAP? Okay. So what NAP gives you is time series metrics. Okay. So if you run the newer versions of NSX 410 or whatever, and you have NAP installed, you go to your edge, we'll give you time series metrics to look at your data path CPU core usage and so on, right? So if you look at other features, as we add new capabilities into NAP, you will start displaying those in the UI for you, okay? But if you don't have NAP or you don't have the newer versions, then you have to get that statistics and monitor it yourself, right? So this is built into on a per edge basis, but if you have a lot of edges, this is hard to monitor, right? So what you can also do is we have custom UI views that you can create using APIs. So in this case, I've created a graph per tier 0, right? So it covers all the edges of my tier 0 cluster. So you can monitor that. Okay? Again, if you're interested in what the API looks like, you can email me and I'll send it to you. Now, this is where I spent most of my time with customers, okay? This applies if you are running, regardless if you're running NSX or not. So what I've drawn here is a hypothetical ESXi host broken down into its components, okay? This host has 2 CPUs, and from a networking perspective, we don't really care about CPU as opposed to NUMA counts, okay? So this host has 2 CPUs, and in this case, each CPU represents 1 NUMA node. So the reason why I've drawn them as NUMA is because there are CPUs, even from Intel, that will have multiple NUMA nodes per socket, okay? If you run AMD, there will be many NUMA nodes per socket. So be aware of what your NUMA topology looks like, okay? And then I've only drawn this host with 1 NIC, and I've broken down the NIC into the ingress side on my right, your left, and then the egress side on the right. So most of the problem on network performance, okay, customers will call me and say they have edge performance issues and so on, especially when they're running VM edges. More than likely, your issue is on ESX networking, not on the edge. Okay, so that's why I spent most of my time here. Okay, so this hypothetical NIC that I've drawn has 12 queues, number from 0 to 11. Okay, and the same hardware is on the right on egress, and I've drawn the same 12 queues, right? But it's one NIC. Now, when traffic enters your ESXi, okay, it'll be hashed to a queue, right? That same flow can only go to one queue at a time, right? Now, before we talk about that part, you see these blue big arrows on the screen here called pole worlds, right? The pole worlds are CPU threads that have a one-to-one mapping to the queues, okay? So when a packet enters a specific queue, it will be read off from the queue. The pole world thread will read it off the NIC queue and send it to your VMs, okay? So what you should realize here is that when that pole world thread goes to 100%, it doesn't matter how fast your NIC is, right? You'll start dropping traffic, okay? So it means that if your VM is using only one queue, the throughput of your entire ESXi host, right? Or if all your VMs, for example, are using only one queue, you're going to be maxed out at one pole world's CPU usage, right? So I've done some measurements with some big financial customers, and in a typical enterprise environment, one pole world going to 100% in a contemporary CPU will max out at about 9 gigs, right? Obviously, at 9 gigs, you're already dropping traffic, right? So it doesn't matter how, again, it doesn't matter how fast your NIC is, okay? A lot of people ask me, can I get more throughput when I go to 100 gigs, right? You don't, because your throughput is going to be limited by whatever the pole world is doing, okay? So how do I get more output or throughput to my VMs, right? So most of you will be familiar with port channels on networking, right? So inside the ESX, on pretty much all NICs, we support this feature called RSS, or receive side scaling. It's the equivalent of port channels for NIC queues, okay? So in this picture, I've drawn 2 RSS bundles. The first one is called default queue RSS, and the second one is net queue RSS, okay? Now, how is this used? When your VM first boots up, okay, it has no traffic on it yet, right? So all of the traffic for that VM will be going over the default queue. Now, in some NICs, the default queue is a single queue, right? In this picture, I've drawn the default queue as an RSS queue. So your traffic to those VMs will be hashed over the RSS bundle, which is 4 queues in this case, okay? Now, when that traffic rate to your VM exceeds 2 megabits per second, okay, or 2,000 packets per second, there is an ESXi load balancer algorithm that runs, that looks at that traffic rate and say, hey, you have exceeded the threshold of 2,000 packets per second. Let me move you out of the default queue into another queue. Okay? So which queue does it decide to move you to, right, or your VM to? It will move it to based on how your VM is configured. Okay? If your VM is configured to request for netqueue RSS, right, this is a configuration that's not enabled by default, but if your VM is enabled for it, the ESX load balancer will move it to a netqueue RSS engine. That means your VM will continue to get RSS support. Otherwise, it will move it to a single queue, like VM 1 and 2 in this case, right? Right? So in this case, if you have deployed 4 edges, right, if you deploy 4 NSX edges on this host, VM edges 3 and 4 will get much better throughput than 1 and 2. Right? They're on the same host. They're configured exactly the same way, but 3 and 4 will get better performance. Right? Now, so in this picture, if I have 4 edges, they're configured exactly the same way. VM 1 and 2 are also requesting netqueue RSS, right? But why are they not getting it? So this is where NUMA locality comes in, okay? The ESX load balancer will not allow VMs on different NUMA nodes to share the same queue, Okay? In this case, VMs 3 and 4 are on the second NUMA node. So if they were the first VMs to get triggered through that 2 megabits per second threshold, ESX puts them on the NetQ engine, right? But when VM 1 and 2 gets the same trigger, because there is another VM on a different NUMA node using the NetQ engine already, they got assigned to a single queue, okay? And then when your traffic rate for your VM goes below the 2,000 packets per second, a minute later, I think it's a minute later, ESX will put it back on the default queue, right? So if you have a system where the traffic rate is a big wave pattern where it goes up and down a lot, it will look like sometimes your VM will get RSS, sometimes it won't, right? So if 3 and 4 went below the threshold, and then 1 and 2, they all went below the threshold, and then the next time VM 1 and 2 were the first ones to request RSS, they would get NetQ RSS, and 3 and 4 won't, right? So from when you're looking at your throughput, it will be very frustrating because it will look like sometimes the performance is random, right? It's not random, it's because of this, okay? On the egress side, if you have enabled NIOC, okay, NIOC is the software engine, by the way, right? So on the transmit side, it will read your packets from your VMs and inspect to see what type of traffic it is before it sends it out. So because it's a software engine, by definition, it will slow down your network, okay? So if you don't need NIOC, don't enable it. But when you do have NIOC enabled, and before I say that, I should say that the ESX egress data path is much, much more efficient than the ingress data path, right? So NIOC will enable transmit queues based on the NIC speed, okay? If you have a 25 gig NIC, it will only enable 2 queues. If you have a 10 gig NIC, it will only enable 1. If you have 100 gig NICs, I think it enables 4, okay? So if it's so much more efficient, why am I even talking about it, right? So if you look at the hardware, even though I've drawn the ingress and egress queues separately, they're actually the same hardware, okay? In order for the NIC to finish sending traffic, it has to go through the same hardware engine, right? So because in this case, queues 0 and 1 are being used for transmit, the fact that I have to complete sending traffic on it means that I have to access the same hardware interrupt on the NIC, right? That will have a corresponding hit on the ingress pro worlds. So let's say you have traffic spread evenly across all your queues. In this case, because queues 0 and 1 are used for transmit, you see that pro world usage for queues 0 and 1 are higher, right? So one of the things that you should look at is whether you should increase more transmit queues, not because you need it for transmit, but basically to spread out the load on pro worlds for receive, okay? This is the same picture. I forgot why I drawn it separately, but it's the same picture. Okay, so this is I don't know how many of you went to Sam's session before this one in room 29. So he talked about NIC tunings and so on, right? The previous slide talked about how you monitor what he configured or recommends, right? These are some of the things that you can do, right? The first part is you have to know what your NIC is and what features it support, okay? Now, most of our customers are running Mellanox NICs or Broadcom NICs, okay? Now, the biggest issue with NICs are that they don't have enough RSS engines to support the number of NUMA nodes that you have, okay? So taking if you're running ESXi7, right? The Mellanox driver for ESXi7 has 3 RSS engines, okay? But the driver only enables 2 by default. One is assigned to the default queue, and the other one is NetQ. So you have 2 CPU sockets. That means some of your VMs will never get RSS, right? Because one is default, the other one is NetQ, okay? So you have to know your drivers and enable the drivers appropriately, right? So let's say you only have 2 NUMA nodes, and you're running Mellanox, you should be able to go in and enable all 3 engines, where 1 is on default and another 2 are assigned to your 2 sockets. Okay? Now, let's say you don't have enough RSS engines. What can you do? Remember, there is a 2 megabits per second or 2,000 packets per second threshold, right? That moves traffic out of the default queue. What we can do is raise that threshold to a number that is so high that it will never be met. So that's what those, the average packet count shift and packet count shift counters do. The 30 is 2 to the power of 30 packets per second. The 50 is 2 to the power of 50 packets bits per second. Okay? So your VM's traffic rate will never exceed that, so that means your VM will be forced to stay on the default queue. So by doing this, what you can do is, because you don't have enough RSS engines, you can force all your VMs to stay on the default queue and enable RSS for the default queue. Or increase the number of queues in the RSS. So by default, Mellanox will have 4, so you can change it up to 16. Okay. The last part here is your VM by default is, remember on the 25K NICs we enable 2 queues, right? But by default, each VM is only allowed to send on 1 queue at a time. Right? Doesn't matter how many flows you have, it will only be allowed to send on 1 queue. So the last 3 options here will change your settings such that your VM will be allowed to send to different queues based on the flows. Okay? And the last row here is to enable up to 4 queues, right? So by default, 25 gig NICs is 2 queues. In this case, I've set it to 4. So you can set it to whatever value you want. Now, if you disable NIOC, the number of transmit queues will be equal to the total number of queues that you have, right? So by disabling NIOC, not only your performance will be better, the number of transmit queues will also be much higher. Okay? Again, I spent 3 hours with a specific customer in the last 2 slides, in the last 2 weeks already, and they still need more sessions. So if you don't get this whole thing, don't worry about it. Reach out to me, and then I can help you out. Okay. Obviously, to monitor your CPU usage, right? Don't worry about reading this chart yet. Okay. You want to monitor your pole world usage, right? Because the pole world determines how much throughput you can get through. When it gets to 100%, you're screwed, basically, right? So in this case, this is actually data from an actual customer that I've graphed, okay, for over 2 weeks. So you should be, there will be 1 pole world per queue, so there will be many pole worlds per ESXi host, right? So I have taken pole world usage from 1 edge cluster of 4 hosts. I think it's 4 hosts or 6 hosts. It's unreadable, right? But you don't need to read that. What you are looking for is the high threshold to see whether you have approaching 85, 90%, right? Again, because network traffic is never steady state, if you're at 90%, that means sometimes you're bursting to 100%, okay? So you'll be dropping traffic. So I tell customers to basically look at this chart and make sure that you're not trending toward the wrong direction, okay? And if you're trending toward the wrong directions, you will be looking at ingress buffer drops on your NIC, right? Now, by default, ESX does not give you these counters, okay? There is a counter called, each of the NICs will have counters called private NIC stats, okay? And these counters are read directly from the NIC A6. So these the outer buffer counters will most likely be depending on your NIC, will be part of these private stats. So you should be looking at that, okay? What else I have? Okay. You call up GSS and you say, my network sucks, right? Don't just call them and say network sucks, okay? Sometimes GSS will go and say, hey, engineering, my customer said network sucks, right? You have to give us data, okay? So if I can get anything across, if you complain about networking performance, collect this data. Otherwise, I cannot help you, right? This is an eye chart. I have 10 minutes. I'm actually pretty good on time, actually. So you don't need to read this. Make sure you get a PowerPoint, this PowerPoint, and get the chart yourself, or email me and I give it to you. This is the day in life of a packet inside ESX, okay? And it's not the most up-to-date picture, but it was generated 2 months ago, I think. But inside ESX, one of the best troubleshooting tools on ESX is packet capture, okay? And you can capture the packet at different parts of ESX. I mean, we call them filters, right? So you can capture at right when it leaves the VM, or right when it arrives at the VM, or right when it enters the uplink or leaves the uplink, and so on. Okay? So this will tell you if you're troubleshooting a network drop problem, for example, you can trace the packet to see where it drops based on the packet capture. Okay? So you don't need to read it. Get a picture when you actually need to use it. Inside NSX, if you are familiar with trace route, right? We have trace flow and live traffic analysis. Trace route will give you router hops, right? Trace flow and live trace traffic analysis or LTA inside NSX will give you a detailed trace of your packet through the entire NSX system, right? Remember the previous chart where I showed you the filter points inside ESX? Live trace analysis will show you multiple hops inside ESX to tell you what is happening inside your packets. The only difference between your trace flow and live traffic analysis is that trace flow will be looking at packets injected by the feature, right? Live traffic analysis is looking at live traffic. So in order to use LTA, you have to know what traffic is running, okay? Now, if you're worried about performance, okay, I'll talk about how to look at latency later, but if you look at the output of your trace flow or LTA, there's a timestamp that's printed with each observation, right? If your packet enters one host, it goes to multiple stages inside that host or your edge, right? Associated with this will be a timestamp, okay? And that timestamp represents, if you just take the difference between the ingress and egress timestamps, you have the latency, right? So you can look at your performance using this tool. This is an example of an output. So I don't have a pointer, but you can see that in this column over here, we have these timestamps, okay? And if your traffic is staying within NSX overlay, it will also give you a nice picture. Okay, if you're running, anybody running NSX 4.x? 4.1? Okay. So especially with the 4.1 feature, okay, 4.1 release, we've introduced something called online diagnostic. If you're familiar with any form of troubleshooting, you go through, let's say, packets not going through your system or whatever, there's a multi-stage workflow that you follow through, right? It's not one command, you run a series of commands. So what online.ods will do is it's a collection of runbooks. We pre-create these runbooks based on what GSS or our support team has told us is common in terms of interaction with customers, right? So we've created some of these runbooks. And it's not only a collection, it's also an execution engine, okay? So you have access to this. So this is an example runbook where we are checking BGP neighbor state, okay? So you can see that if you were to do this manually, right, you have to go through each of these steps on your own individually. ODS will run it for you if you just give it the peer IP address, okay? It'll give you a step-by-step output of each of these, right? And then it'll also produce something, all these outputs for you, right? We call them artifacts. So you can collect the artifacts and give it to your support team, and then they'll be able to help you out better, okay? Latency monitoring, if this is enabled at a transport zone level, right? Because this only works if you're running Geneve overlay, right? If you're not running overlay, you're running DVPGs only, this won't help you. So inside Geneve, one of the reasons why we left VXLAN from NSXV and went to Geneve is because the Geneve header is extendable. Okay? So what we've done is, inside the Geneve header, we've embedded metadata that have timestamps for the packets when they leave or enter each transport node. So we're able to tell you how much time has expired between observation points in the NSX system, right? So if you enable this capability, we'll export these stats into Verni, and you can view your network performance through that, right? Essential CLI, I'm not sure. I have a lot of customers who are familiar with it. So what you can do is a lot of people have, they disable SSH into your ESXi host, your edges, and so on, right? But if you have access to your NSX manager, you can SSH into your NSX manager and run all of your NSX CLI commands to your remote nodes through Central CLI, okay? That's it. I'm on time, actually. Questions?